So by now, I hope you have all understood how to write down the effective operators. I mean, depending on the type of physics you are doing, and so what I will do, I will tell you how to connect the physics at different scales, and you see, I will talk about connecting the high energy scale to the low energy. Low energy you know that there are many low energy experiments are going on, and we have a large amount of data. So basically, this kind of exercise, either top down or bottom up approach, like if you can constrain the info, if you collect the information at the low energy and you can transfer it to as a information to the high energy, that will give you some sort of idea what to do at the high energy experiments, and the vice versa. If you find something at colliders at high energy, that will also help you to get some idea by this method. Like that will be the top-down approach. So collecting the information at high energy, transfer it to the low energy sector, and see what are the effects you are getting, and try to check by experiments. Okay, so these are basically complementary things. So what I will do in this talk, basically, I will discuss about how this mechanism work. Okay, so as you know, that effective field theory is basically you can write down your set of operators at different scales. You can integrate out particles and of your choice, and you can just you pick up the particles whatever you are interested in, and you can write down the operators in a gauge invariant way. Okay, so this is what the effective theory, and why this is useful now by now, because you know that standard model is successful. It's a successful theory, and by now we know how to generate the masses for the standard model particles, and also we know actually we also know that it is clear to us the CP violation picture in the standard model. So a couple of things, I mean many things we know by now, and standard model, and in fact after the discovery of Higgs boson, it is more or less clear all the particle content of standard model by now we know. However, there are a couple of questions are left unanswered. It's basically, you know that the existence of dark matter, neutrino mass, various other things are there, like why the CP violation that we see, like the baryon asymmetry that we see in the universe, that's also you cannot explain by the standard model CP violation. So these are some unanswered thing which needs to be answered. Now, therefore, what you can conclude out of this, that it might be the standard model is an effective theory, and it's valid up to some scale. Let's say you can pick that scale to be lambda, which is the new physics scale, and beyond that you can add additional degrees of freedom to the system, and you can write down your set of operators again, and you can do the things. Okay. So now, so far we have not seen, as you know, we have not seen any evidences beyond the standard model. So in that, I mean, so that you can, that you can try to understand by assuming that maybe the couplings are very weak, or the new particles that you are expecting is very heavy, so that you cannot with the current setup in the experiment, you won't be able to detect it. So if it's too heavy, then you can still live with the particle content of the standard model, and you can extend your reach to a high scale, and you can, at the high scale also, you can write down your effective theory. Okay, and that is what is the SMEFT, right? So basically that's what I mean the trick right now we are using. So, and as we know that operator coefficients, that while you write down an operator, set of operators, definitely you have to introduce the coefficient, and you know those coefficients will be scale dependence. It will be sensitive to the scale that you are working in. Okay. So that's precisely the interesting thing that will help you to connect the physics at different scale via those Wilson coefficients, okay, or the coefficients of the operators. Okay. So, like therefore, it is useful to study the running and the mixing of operators coefficients, and like you can start with BSM scale, you can run it to the electric scale where the experiments are going on now, and also you can further connect it to the low energy where also you have lot of data and further experiments are going on. Okay. So, so therefore, that is the idea. So, and as I said, we have lot of data available in the low energy sector which can be utilized to put constraints or to understand the physics by what would be the probable physics from low energy to high energy. Okay. So, that is a possible way. So, now as you have seen that here I will try to connect the coefficients at SMFT, like standard model effective field theory, where you know that it's up to 1 TeV, let's say, since we have not found anything up to 1 TeV, it allows us to parameterize the effects of new physics in a high dimensional gauge invariant operator. That's what we call SMEFT, and you know the gauge group is the standard model gauge group. Particle contents are also standard model particle content. So, you following this gauge invariance, you write all possible operator, okay, following various other things. So, I am not going to detail of those things, you know there are papers on it. And so, what do you do here? You are assuming that you have integrated out the heavy scale physics, heavy like new particles that you have, you are integrating out those things, and all standard model degrees of freedom should contained within the framework, and either it may be the fundamental particle or it could be also the composite fields. So, therefore, what you do? You write down the SMFT as like your standard model effective theory, and then you have a tower of operators, high dimensional operators. That is what you do, right. So, so these are basically all the operators are written in terms of the standard model particles. Okay. So, this is what is SMFT. Alternatively, what you can do, like it's alternative and also the complementary to whatever you do here, you can do similar thing to the low energy sector. Okay. So, that will also help you, as I mentioned, to search for new physics. That is called low energy effective theory, or this is also sometime in the literature used as weak effective theory. Okay. So, it's the operators here will be written below the electric scale. Okay. So, that means you can understand then below electric scale mean few particle content you are removing from your list, right. So, that means you will be removing W, Z, Higgs and top. Okay. Rest will be there. So, therefore, so symmetry group would be SU3U1 because you have all the SU2 content, it is not there, and that is what the LAFT Lagrangian will be. So, it should be QCD, QED interactions, all the QCD, QED interaction in the standard model, and then you have some the term 3D operator which will be useful for Majorana mass generation, Majorana mass term, and these would be the high dimensional operator which are greater than greater than equal to 5. So, so this is what the QCD, QED. So, you see the particle content, you do not have here the top, and so all the other fermions are here, and then you have this part. Actually, you can write as a combination of two, right. Like one part would be simply electroic part that will be coming, you can assume those operators will be coming from integrating out the W, Z and top. Okay. And the another part you can add another set of operators, those might be coming from the other new particles, those we do not know. Okay. So, so that way you can divide this part in two sectors, like one is electric and the other is BSM. Okay. So, and for the electric sector, the calculations are readily available. I like, you know, a famous paper by Buras. I mean, you see for the how to do the running and how to connect the coefficient from electric to low energy and all these things. For this, electric sector is known, like the part associated with integrating out W, Z and tau. Okay. And so now, what would be the dimension? This, if you do power counting, this the coefficient should scale like 1 by V, okay, or 1 by V, D, exactly if you write it, D minus 4. Okay. However, if you are obtaining this, it is possible that you will be obtaining those effective operator via the insertion of SMFT operators. So then power counting will change. So in that case, that would be the power counting, right? So you will have additional 1 by lambda factor, and that additional lambda factor you can write like 1 by V by lambda, and then this whole power counting of this quantity of this coefficient would be like this. So you will have additional suppression factor that is coming from the that is coming as a V by lambda. Okay. So now, so therefore now what will how does it help you? Basically, once you I mean this you can utilize RGE, and these coefficients you can bring down to very low energy from the electric scale, and that you can utilize for further study. Okay. So that's the basic idea behind all these calculations. Now this is the flow chart. I mean, like how exactly to do the actual calculation. Okay. So like low energy to high energy or high energy to low energy. Okay. So various steps are there in between. So you can see, let's say you have some new physics scale which is not known to you. You put it at lambda, and you don't know what is the Lagrangian also. But once you know this, once you have a UV complete model, then you can do a matching of this UV complete model to your SMFT basis. Okay. And then further, what do you do from here? This is your SMFT basis. So set of SMFT operators, you know 59 operators are there. So you can write it down, and then what you do? First step would be you do a RGE, trigonometric group evolution. That will basically you can run down these coefficients to electric scale. Okay, that's the first step. And then what you can do at this scale, electric scale, you can match it to the effective operator associated, which should be relevant below the electric scale. Okay, so that matching you can do at that scale. Okay. And then, so this is your this is where you will be defining your low energy effective theory basis or weak effective theory basis. Okay, so that's matching you need to do. And then what you will do from here to a very low scale will be again you will be using RGE. Okay, so that means from electric scale to this you will be you need other, because here the operator might mix. Okay, if you don't do, if you directly come from here to here, you may be missing those operator mixing and all these things. Okay, also so this is one of the important point, that operator mixes here, this set of operators, among them they mix. So that contribution is relevant. At the same time, what is relevant is you might need to consider the running of QC decoupling and the QD decouplings, because those, you know, if you, while you are going to a lower scale, they vary abruptly. Okay, so while you are going to a very low scale, you need to be careful about the running of the QC decoupling in particular. Okay, so you might need to consider that as well in your calculation. Okay, so this is the flow chart. Okay, that's how if you understand this, you are done. At least from basic understanding point of view. Calculation is much more difficult, so that part is different. But at least understanding point of view, it will be done up to this. Okay. So now, how exactly this thing could be done in a realistic scenario? Like consider like RGE like for the operator coefficients. So like I have written down this equation for SMFT basis. So you know 59 operators. So in principle, this is how you can write down the running equation of RGE equation for those set of operators or for those set of Wilson coefficients. So here gamma is basically the anomalous dimension matrix, right? That is needed for the understanding of the running of the coupling. Okay, so that's the one of the important part in the calculation. Okay? That you need to understand how to calculate. Okay, so this is what this basically tells you whether there are operator mixings or not. Okay. Also, I mean, it will basically give you an idea how the things are running from one point to another, how exactly they are connected. Now, what is that? What is this gamma? How do you calculate it? So, gamma is nothing but you can define it like this, where Z is basically the operator renormalization constant. Okay. Now, this is how you define the renormalization of the Bayer operator. So, Q, let us say Q0 is your Bayer operator and Q is your renormalized operator. So, Z will be the renormalization constant. Okay. So, then so let us say what is this basically, how do you define this renormalization constant? If you define an operator, let us say you define a 4-quark operator. Okay. So, what you need to do, this is the matrix element, so matrix element of the 4-quark operator, and then what do? You will do corrections to this 4-quark operator. Okay, you will calculate the corrections, and those corrections, higher order corrections, might have divergences. Okay. Now, the question is that how do you deal with those divergences? Now, those divergences you can absorb as a renormalization of the operator. So, within you define the renormalization constant, and within that constant you absorb those divergences. That is the procedure you can follow. Okay. So, therefore, the divergences here, whatever you will be getting from the loop calculation, you will absorb in the coefficients within the renormalization constant, and this is how you do. So, what do you have? While you are writing a 4-quark operator, you will have quark renormalization as well, right? Because those quarks are Bayer quarks. Okay. So, they are in the interaction base. So, basically, you use the renormalization for the Bayer quark. So, ZQ is the wave function renormalization. So, you have 4 in total. So, therefore, square root of Z for 4, it will give you Z square, okay, ZQ square. And Zij is the operator renormalization that you are absorbing, that you are introducing. So, therefore, whatever the divergences you have within the matrix element of Qj, a part of it will be cancelled by ZQ minus 2, and the rest you will absorb in the definition of Zij. So, that is the technique of introducing this thing, of utilization of how to utilize this operator renormalization. Alternatively, you can view it differently as well. This operator renormalization you can transfer as a counter term of the coefficient, Wilson coefficient here, right? Because you know what you need to do, you need to just define a renormalized quantity which is the product of this C I and the matrix element Qi. Okay? So, that is what you need to do. So, therefore, whatever you defined here, it could be also alternatively could be defined by renormalization of Ci or counter term associated with the Ci. Okay? How do you do it? You can understand it clearly. So, let us say you introduce, instead of the operator renormalization, what you are doing? You are just defining a counter term associated with the coefficient Cj, and as usual you have the wave function renormalization associated with the quark. Okay? These are the two things you are introducing. So, now what do you do? This thing, whole thing, like Ci, Qi, you will be writing like it's a 4-quark operator again, let us say we are considering. Then you have ZQ square coming from the quark renormalization, and then you have Zijc, that will be the counter term you have introduced here, or the renormalization parameter that you have introduced here, right? So, then this thing you can write in this form. Okay? It's just simply addition and subtraction. So, then this would be the renormalized one, this quantity, and then this you can treat as a counter term. Okay? So, this is how you can, the whole thing you can play. So, now once you do so, then the whole thing Cj Qj, basically what you are calculating, this you can write in this form. So, here you are not doing any kind of operator renormalization, instead you have introduced a counter term associated with the coefficient. Okay? So, then finally, in one way, let us say in the beginning, this part you have obtained from operator renormalization, that part you have obtained from the coefficient renormalization. So, these two things should be equal, right? Because anyway you are talking about the renormalized quantity, this quantity you are talking about. So, if you compare these two things, then you can say Zic like this renormalization constant associated with the coefficient should be equal to Zji inverse. Okay, so that means that should be equal to the constant associated inversely proportional or equal to the inverse of the operator renormalization constant. Okay, so that means these are connected. So in a way, if you have calculated one, you will be able to easily transfer the impact of it to the coefficients. Okay, so what do you need to do therefore in order to calculate the anomalous dimension matrix? Because this thing would be associated with the anomalous dimension matrix. How? You know that I mean this equation you are familiar with, right? Mu dc mu this Ci is the bare coefficient, let's say. Okay, so mu dc mu will be 0. So that dc mu Ci you can write from this. Okay, and Zij you can simply split like this, delta Ij and delta Zij. Delta Ij, because this is necessary, this will be, first term will give you the actual coefficient and that will give you the corrected term or the counter term associated with the coefficient. Okay, so therefore if you write it like here, if you substitute it here, then this equation can be written like this. Okay, so mu del Ci by del mu minus mu this quantity, and this is what is gamma Ij Cj. So gamma Ij is what we have written down earlier as anomalous dimension matrix. Okay, so gamma Ij, how do you calculate therefore? You need to simply calculate these derivatives, okay, of the derivatives of the renormalization constant, which you are, or renormalization of the renormalization constant of the operator, I mean constant of the operator renormalization. Okay, so this Zij is basically, you can connect it to Zij inverse. So basically once you calculate the operator renormalization constant, then you are done. You will be able to calculate the anomalous dimension matrix. That's all. Okay. So now just take an example, you take an SMFT operator here as an example, how to exactly calculate those matrix. You can realize. So let's say this is the operator, and then you are taking the corrections at one loop level. Okay. So these are the corrections. These are the diagram, one of the diagram, important diagram, leading order that will contribute, and definitely this will have a divergence. Okay. So now how do you absorb this divergence? This divergence you can absorb by defining a constant counter term like this. So this factor here, so you are adding a counter term, and this counter term is defined such a way that, I mean, that so that the divergence here, UV divergence that you have will cancel. Okay. So now you can also introduce, apart from ZB, apart from the constant associated with Cj, you should also introduce the renormalized coupling as well as the renormalized fields, right? So all these things you introduce, and finally renormalized, I mean the effective coefficient that you will be getting is basically this quantity. So taking into account all the wave function renormalizations. Okay. So and this you can utilize to calculate the final anomalous dimension matrix. That's all. Okay. So now we'll, as an example, you can think of like 4 fermion operator. Okay. So this is the interaction vertex. How do you write? And then counter term you will be able to calculate if you calculate the wave function, all the correction in external legs. You calculate all of them, that will give you the counter terms, right? So and then you calculate the corrections at first order, one loop corrections to all the this effective vertex. So issue all possible corrections. This is with photon, and these are all with the gluons. Okay. So then you just all these corrections, if you this will contribute. So adding this with this will contribute to your anomalous dimension matrix. Okay. I mean it will contribute to your operator renormalization, but finally you can convert it to, you can calculate from there the anomalous dimension matrix, right? Similarly, if you consider psi square x, this kind of operator, it's like you can also calculate here the counter term by calculating the corrections to the external legs. Okay. And then finally you can calculate the vertex interactions to this operator, like with gluon and with photons, okay, and this will contribute to psi square x. You can see it already. Also, it can contribute to psi square, but for that you need to use equation of motion, okay. And an additional thing, like this set of diagram will contribute to this operator, and this set of diagram will contribute to this operator here. So, but similar, this whole thing will contribute to psi square x as well as psi square. So, this will in a way will contribute to operator normalization, as well as finally it will be converted to the anomalous dimension matrix, okay. So, this is how this set of things I have written down for LEFT basis, okay. So, suppose you have LEFT operators, set of operators with fermions, and for them you can do the corrections with photon and gluons, okay. So, now matching. So, next thing, as you remember the flow chart, I mentioned at one step you need to do the matching, okay. So, goal of the matching is to find out the coefficients at different order, okay, in a fixed order perturbation theory or in any kind of matching calculation. What you do, the idea is to find out the coefficient at a different scale, right. So, so here what do you do basically, what do you need to do? You need to just equate the amplitude, okay, at LEFT, whatever the amplitudes you are calculating using LEFT basis of operators, that you can equate with the SMFT basis things, but all has to be renormalized, okay. So, you need to add counter term and the full other whatever the one loop or leading order or whatever results you have, you need to add them and you need to equate them, okay. So, this is what finally you can write down. So, you have 3 contributions, then you are adding the counter term that will partly cancel the divergences in your loop, okay. And here also you have SMFT tree, counter term, and partly it will cancel the divergence of things, and the overall divergences, leftover divergences is expected to be cancelled within the whole thing, okay. In a proper things it should happen, okay. Otherwise you need to there will be problem. I mean, you need to rethink, or you are missing something or something else. So, in general you should expect this. However, in this case basically while you are matching doing a matching calculation from SMFT basis to LEFT basis. So, that means what you are doing, you are equating a different operator contribution in SMFT to a single operator contribution in LEFT, right. So, therefore, this is the matching equation you should write. So, Cij or Qj matrix element that you are calculating SMFT, it should be equal to a contribution or amplitude at LEFT. Let us say this I am indicating with I mean the operator, the single operator that I am targeting in LEFT basis, and that if you expand the left hand side, this would look like this. So, Cij, this would be the tree level contributions. If you have a tree level operator, I mean if your operator here, if you have some operator in a SMFT basis which will contribute to the LEFT things at tree level, then you will have some Cij 0, and then you need to add Cij at one loop level. That means the contributions that are from the SMFT operator, those are coming that will contribute to LEFT at one loop order, those part, and then you need to add the counter term, okay, that should be associated with the tree level operator, okay. So, this is how, if you expand this is left hand side will be associated with this, would be with the part of the coefficient that should be convoluted with the tree level coefficients, matrix element is given by this, and another part would be like if you do corrections to the effective operator, one loop corrections to the effective operator. So, when that would be relevant? When you have a Ci0 0, that means you have a tree level coefficient, I mean you have an SMFT operator which will contribute to your LEFT operator at tree level. So, in that case, if you want to do a one loop matching, you need to calculate the corrections at to these operators, SMFT operator at one loop level, which will contribute to your LEFT things. So this is what the perfect matching calculation, you have to do it in this way. So fixed order things, fixed order theory, you have to just order by order, you have to calculate all the things, and then you need to match from both sides. Okay, that's the whole idea. If anyone have any difficulty, just this part is crucial. Okay, anyone have any difficulty?
Can you please take the last part?
Last part. So you are doing a calculation, let's say matching at one loop level, right? So one loop level mean, okay, let me write down. So in general, what do you do? So let's say I'm just talking in terms of, let's say, full site. Forget about for the time being SMFT or LEFT. Let's say you are doing a calculation where you have a full theory, okay, and you have an effective theory, okay, and you are doing a matching calculation. So in general, what do you do? So full theory, renormalized things. Let's say this is your tree level of contribution, and then you have one loop order contribution, okay, at one loop. You have some coefficients here, let's say, I am not writing those things. That you will be equating with the operator, let's say C, let's say CO, okay. So, but remember this C has to be C at leading order plus C at one loop level, okay. And then your effective operator, you need to write down O at leading order tree level, and then O at one loop level. This is what the actual matching equation should be, okay. Now you expand both sides. You expand both sides, what do you have? M0, you will be getting like C0, O0, okay. Now if you write M1, or M1 would be what then? M1 would be equals to, because you remember these coefficients, whatever the coefficients you have here, here also you will have similar coefficients. So that means this will decide the order of the calculation, right? So that means now if you talking about, and also this will also have the similar coefficients. So fixed order mean this order you are matching, and this order also you are matching. So that means same coefficient, same similar coefficient I should equate, right? So that means M1, okay. So that should be equals to therefore C1 0, right? And then you have C0 okay. That's what one of the term I have written down here, okay. So once you understand this, then you will be able to do calculations. Only thing is that loop, you need to learn how to do a loop calculation. So here I will take few examples, like one of the interesting mode is B2S. It's a efficiency process, and standard model is suppressed. So that's why we have a lot of expectation from this mode. So the SMFT, these are the set of operators in the SMFT basis, which will contribute to B2S at tree level, okay. So you will have a tree level operator which can contribute to B2S process. In general, I am talking about B2S. I will subdivide this thing like various mixing or semi-electronic decay and so on. We can do that later. So here note that all the operators are written before the unbroken phase, right? So that means you did not have the operators are written in interaction basis, right? So you need to transfer it to the mass basis, because below electric scale while you will be transferring it, you will be doing it at the broken phase, okay? So that means you need to transfer it to the mass basis. So what do you need to do for that? You know the mechanism, right? You need to rotate the flavour, okay? So and that's what you need to do, and finally part of it will contribute also as a CKM element, but in general I am keeping it like just the rotation of the fields, okay, from interaction basis to the mass basis. So now for an example, like if you have an operator from here, like this is the operator written from here, okay. So for that, if you introduce this rotation, so finally your coefficient should be like this. Okay, so it's just the actual coefficient what you have in the interaction basis, that should be somehow multiplied by this factor that you have here, the matrix that you have here basically. Okay. So so this is what you get. Now what I will now I'm going to, like, first thing is BS bar mixing. Suppose you know what is the BS bar mixing, right? So so this is the effective operator in LFT that will contribute to BS bar mixing. So these are the set of operators you see. So BS bar mixing, simple tree level you can have, also you can have loop level contributions. Okay. So so to BS tree level also they can give you BS bar mixing, or it can come via loop, additional loop diagram that will also contribute. So here I will talk about both the things, like tree level contribution and as well as the loop level contribution. So these are the set of operators which will contribute at the tree level. Okay, or in general, this is not what I mean by tree level. This is what I am saying. These are the in general the basis, LEFT basis. The operator is written here. Okay, so the prime things you will be getting if you transfer PL to PR. Okay, in this set of operators. So now, what are the operators that will contribute to this basis or BS bar mixing at tree level? You can see from this list. So these are the operators. So you can see if you expand this, you can easily get BS bar vertex. Okay, all these operators can give you. So that means it can contribute at tree level to the BS bar mixing. Okay. So and if you do a simple matching, like if you just write down the operators and rotate the fields and match it with this operator following this, because it's a tree level thing. So tree level you don't need to write down loop part. So it's a straightforward matching. So like this equation. Okay. So and if you do so, you will be able to get this Wilson coefficients. Okay. And this I am getting by using, you know, this the relation of the product of the generators. So this is give you a color suppressed contributions. So 1 by NC is coming from, these are QCD I mean so generator of SU3. So you have this property. So these are color suppressed contributions 1 by NC, but this is coming from Q8 only. You see you have TA here. And apart from this, I mean this again the coefficients as I mentioned will be obtained from the actual asymmetry coefficients by these rotations. So you just by this S. So actually you can get it. If you do a simple calculation, you will be able to reproduce it. And then there are other contributions which are relatively suppressed. Those could come from this operator here. You see, if you expand this phi, so this will also contribute to a leading order to the masses of the fermions. Okay, and then this is the corrections, and corrections will give you BS vertex. Okay. So that means this effectively will contribute to BS bar mixing as well. But these are relatively suppressed things. But here you see only these are the set of operators which will contribute. You don't see any contribution from C3 or C3 prime, and yeah, rest of the things are contributing. However, why do you need RG or running? That you will see in a while. If you calculate the RG, you will see because of the operator mixing, C3 will also contribute. Okay. So that's the importance of RG. So you will see in a while here in this slide in particular. So this anomalous dimension matrix will be only as you have seen the corrections that you are calculating because of gluon exchanges and photon exchanges. So basically it will contribute to your operator normalization here. This part references I will provide, you can check from there. And so these are the diagrams effectively that you need to calculate. Okay. So you have 4 quark operators. All the operators that you have seen is a 4 quark operator. So you can calculate the corrections to QCD and QED corrections, and so basically that will give you the anomalous dimension matrix once you calculate all these diagrams. And if you then you write in matrix form and try to derive the anomalous dimension matrix, you see here this would be the form, and you see here it's mixes, right? So you see 2, 3 is mixing. Also here here it should be like this, and this operator is also mixing. Okay. So in alpha S as well as in alpha electromagnetic in QED, all they mixes. So that's where the role of RG is there. So basically, whatever if you have a direct matching, if you don't do the running, you may be missing the contribution of the operator. That is basically will contribute by RG. Okay. So this is one of the thing, and one loop level. If you try to calculate the one loop level, so these are the set of operators. Here it's written, which will contribute, part of it will contribute at one loop level to BS bar mixing. Okay. So here I pointed out this set of operators which will actually do the job. So here you see the diagrams basically. So this is the operators here. You see QQ bar and UU. So here these are basically up type quark. So here the contribution will come from the top, and you have a W exchange here, and this all these four operators can contribute here, and actually one can calculate the coefficients here and do a matching calculations. Okay. So if you do the matching calculation, this would be the operator to this would be the coefficient to which this will contribute. Okay. So and here IXT is the enameling function. So you see, is the scale is here basically involved is MW square and mu W square here basically. Okay. Since you have just calculating the matching calculation at the electric scale. Later you can, if you run it down to mu B, then that scale will be introduced later. Okay. So now another example is B2S LL. I know this is also an interesting mode, and B2S gamma. In particular, these are also efficiency processes and rare processing, and standard model is suppressed. Okay. Now in this case, in general LEFT basis or WET basis, you can write down a set of operators which are I have listed here. So most relevant are the one which is written here. So you see in general we write it like 07, 08. You have seen in the literature probably 09, 09 prime, 010, 010 prime, and OS, OP, the scalar and the tensor operators here. And you see the primes are basically related to non-prime things with the PL replaced by PR. Okay. So that's how things are distinguished from one another. And these are the operators. You can see here directly you won't get B2S LL, but in general QQ can form a loop, and then finally you will get a JAD or photon, and that will give you finally LL bar. Okay. So that's why you can get a contribution to B2S LL from this set of operators. Okay. In general, you can generate this set of operators. So these are all these operators are written in LEFT basis. Okay. You don't see any other particle. So so what I will do, I will not talk about this set of operators. Actually, then it will be a huge numbers of huge number of operators are there, and a lot of contributions you need to track down. So I will just focus on this part, which are the most relevant one. So here again I am bringing back this set of operators which will contribute to your B2SLL at tree level. First we will discuss tree level contribution. So so one by one we can go, like if you focus on these operators. Okay, you have QQ bar. This will give you a this can, if you expand it, it can give you a BS bar vertex, and then you have lepton L plus L minus you can get from here. Similarly, this operator also can give you a tree level B2S LL. This operator also can give you tree level B2S LL. Okay, so these are the set of operators where you have the quark current contain a left-handed quark. Okay, left-handed quark current basically V minus A type. Okay. So that's why it's contributing to C9 and C10. If you recall the operator, it was PL in both the cases. Okay. Now if you write down another set of operators like this, so you see here the quark current is right-handed. Okay. Here also the quark current is right-handed. Okay. And this will contribute to your, at tree level, it will contribute to your C9 prime and C10 prime. Okay. And then you look at this operator. This also have a tree level contribution to B2SLL, and this will be, I mean, you can have like CSCP and or CS prime or CP prime. All to all this it can contribute. Okay. Then you have another set of operators which will contribute to B2S gamma in particular, or it will contribute to C7 and C7 prime. This you see, this will be via W corrected diagrams. So it will be via loop in general. but this will contribute to, I mean, but in general these operators, one of them is B2S gamma you can easily get like this operator, and this also with a W correction, W vertex correction. And another set is this one, you see d mu you have. So, d mu mean the covariant derivative, if you write down you have Z there. So, basically this will contribute to C9, C10 or C9 prime, C10 prime via this effective coupling BSZ. Okay. This you can get from this set of operators. So, these are all tree level contributions to B2SLL. And then anomalous dimension matrix, if you want to calculate, you need to calculate all these diagrams. Okay. And you will have a set of anomalous dimension matrix. Look at this reference if you are interested to check it. Just look at this reference, they have calculated explicitly all these contributions. Okay. So, these are all you see corrections to the 4 fermion vertices. Okay. And here these are corrections to the all the other type of vertices. Okay. Here is these are all 4 fermion vertices, right. But these are different kind. These 4 fermions, these are also 4 fermion, but different type of operators are there. And also you can have like gauge dependent things and all these things. So, detail you can see here. So, I am not going to discuss it here. But now you can do you can talk about one loop matching. So, at one loop level, you can distinguish different set of operators, like you may have 4 fermion operator contributing to a 4 fermion operator like BSLL. Okay. So, like here you have you see here you have a 4 fermion operator like this, which will contribute at one loop level. This you won't get at tree level, it won't contribute to B2SLL, but you have a TT bar here, TT bar and LL that will contribute to your B2SLL in general. So, this is one loop contributions. Okay. So, these are the if you calculate this diagram, this would be the contributions. Okay. So, here enameling functions is there. And then you can have other type of contributions where you have only let's say instead of lepton, if you have 4 quark operator. So, 4 quark operator in general it can give you directly you cannot get a diagram like this which will contribute to B2SLL, but you can have like BS and then TT bar, it close the loop, and then you have a Z, and then you can from Z you can generate LL. Okay. So, that way it can contribute to B2SLL process at one loop level. Similarly, you match it to effective operators and you calculate following this method, you calculate the coefficients. So, this is the another set of coefficients that will contribute to your B2SLL. Similarly, you can calculate like right handed Z coupling. So, here you see TT bar Z. So, similar thing TT bar Z, this will also contribute at loop level to this O9 O10 operator. Okay. So, this is the diagram, relevant diagram. So, you can calculate, you can check the reference that I mentioned for the calculation. Another set of operator that will contribute to 07, 08, you see the operators here. So, you have TT bar loop, I mean BSTT bar. So, you can see here with this is the kind of operator, you can use PS transformation to get a operator like this, and this will contribute to finally to your B2S gamma. In principle you can from gamma you can also extract L plus L minus, that will contribute to your O9 O10 as well. So, but do the calculation and you can match it and you can get the coefficients. Another set of operator like this kind of vertex, these are the effective vertex here, SMFT vertex, and this again we can draw the diagrams, you can calculate it, and this is the kind of operator that I am inserting here, and this also will contribute finally to B2S. So, you can see finally all these things will contribute to 07, 08, B2S gamma G and all these things. Okay. Another finally you have another set of operators like magnetic operators. These are this operator. This can contribute to all these 4 Wilson coefficients. So, the diagrams are, these are the set of diagrams. In principle, you can have so various, you see all the operators like with a Z here, Z gamma G, and you have with a W, this operator will contribute in this vertex. So, with a W you see here this and this. Okay. So, and other things are from this operator. So, again you need to calculate all the diagrams and then follow the matching equation and extract the coefficient. That should be the idea. And finally, once you have extracted all the coefficients, you do the running. Anomalous dimension are given, you just use those anomalous dimension calculated, or if it's not calculated, you can do the calculation in principle following the method that I discussed, and you can get the coefficients at the from scale mu w, mu electric, to the mu a lower scale. It could be, in this case, it would be the bottom mu b you can introduce, MB scale you can introduce. So in general, finally in the applications, what do you do? Let's say if you have a set of operators, it's been calculated already. So these are the set of operators that you have that contribute to B to SLL or B to S gamma, and for all these coefficients, the gamma matrix, that means the anomalous dimension matrix, are calculated, and this is what the equations. So you can relate, therefore, one of the operators from at a scale mu b, the coefficient at a scale mu b, to the coefficient at a scale mu z, mu equals to mz, that means electric scale. And further you can do one step more running from electric to your lambda scale, and you can get you can relate this coefficient to that scale as well. So that's how you need to connect from one scale to the another scale, following here a two-step matching calculation. Okay, two-step you have to do, as I mentioned, otherwise you may miss the operator contributions from the operator mixing. Okay, so these are the references from where which I consulted to prepare this lecture. So you see, I mean, one with low energy effective field theory, the operator and matching, anomalous dimension matrix calculation by Manohar and his collaborator, and also like specifically for B2S and B2C, the matching to this sector is by Christoph and his collaborator, and this is also by Christoph and his collaborator. So it's a this is for anomalous dimension matrix and all this thing. So that's where I will end. I will not conclude anything. So just only thing is that you have to do calculations to get things under control. Okay, thank you. So I was very much clear, or feel free to ask question, no problem.
Sir, in the basis where you have defined the NEFT and SEFT and you have connected the scales in terms of V.
It should be M by V, yeah.
So is it necessary to do in terms of V, or we can just directly write in terms of lambda?
No, directly in terms of lambda, how do you write? You do not have the scale lambda at all. In you have your scales are defined up to electric, right? While you are writing LEFT, you do not have lambda in your calculation.
So yeah, so only way we have to.
Your upper scale is electric scale.
Okay. Thank you.
So higher scale is V. While you are taking the SEMFT, you are getting the contribution from SEMFT insertion, then you have no choice. It's automatically coming, and then you are just rescaling it in a different way so that you can see the additional suppression.
Okay.
More questions? If not, then let's thank the speaker once more. And we have the honor of felicitating Soumitra, and I would like to do that.